Greetings and salutations, magical chemists. Now that we know how to calculate the pH for weak acids and bases, let's talk about how you would calculate the pH of a mixture of weak acids and bases. Luckily, if you have a mixture of acids, only the weak acid that has the largest Ka value will contribute an appreciable amount of H+. So that's what we're going to use to determine the pH, and we're just going to ignore the rest of them. Fun story, we've actually been doing that already. We've been doing it with the auto-ionization of water. So water, of course, can dissociate to produce protons and hydroxide. But the Kw, as you know, is 1 × 10 to the negative 14th, really dang small. So even though we've been producing protons from water and we've been producing hydroxide, it's usually so much less than the amount of either protons or hydroxide produced by the acid or base you already have, so we've just been ignoring it. And that's what we're going to continue to do. Okay, let's go ahead and try a practice problem. We have a solution containing 1 molar, I believe that's hydrocyanic acid, which has a Ka of 6.2 × 10 to the negative 10th. And then we've got a 5 molar solution of nitrous acid with a Ka of 4 × 10 to the negative 4th. And we want to know the pH of the solution. Of course we do. Well, remember, you have multiple acids. Look for the stronger weak acid. And in this case, if you have a basically smaller negative exponent, negative 4, that makes nitrous acid stronger than the other acid. So that's the only acid we actually need to use in our calculation. That means that this is just the normal pH calculation using a single weak acid, which is what we've been practicing. So, I know you know what I'm going to say. You're going to go ahead and try this on your own. You are welcome to either do the rice table or skip the rice table according to the shortcut we looked at, but let's see if you can calculate the pH. And if you get stuck or you're ready to check your answer, unpause the video. Okay, I've gone and put together the dissociation reaction in the rice table for you, but remember that this is optional. It is not required to earn credit on the free response, unless, of course, you need it to correctly write out the Ka expression and plug in terms of X. Of course, all the work you do afterwards, including justifying your X's negligible approximation, that is required to earn credit on the free response. So we're of course going to substitute in terms for X, and then we're going to solve for X, which gives us the concentration of hydronium. Of course, once you solve for X, then we take the negative log, since that's the concentration of your protons, and that will give us the pH. So the bottom work, the setup and the calculations, these are the requirement to earn credit for a problem like this on the free response. Okay, now that we've seen what a calculation of a mixture of acids looks like, let's talk about polyprotic acids. These are acids that have more than one ionizable hydrogen. So it turns out they actually ionize in steps, 1 hydrogen at a time. And each one of those dissociations has its own Ka value. Now, as each proton is removed, it gets harder and harder to remove another proton. That means the remaining acid gets weaker and weaker. So if you have an acid, let's say you're looking at phosphoric acid, it has 3 protons to get rid of. And every time it loses a proton, it's got a new Ka value that's even smaller than the previous Ka value. So the Ka value for the first proton removed we call Ka1. For the second proton is Ka2, and so on. It is important to recognize that Ka1 will always be greater than Ka2. It's harder to remove a positive from something with a negative charge, right? Positives and negatives are attracted. And then of course that means Ka2 is always going to be bigger than Ka3. So when you have a polyprotic acid in solution, that means you have a mixture of multiple weak acids. However, calculation-wise, because the first one is the biggest, that's the only one we would need to do math with. So that's why we have this order posted right here. And of course, the biggest one, since we only care about the largest Ka value, is the one we use to calculation. Usually, the difference between the Ka values is so big, the second ionization doesn't affect the pH. So, for 99% of polyprotic pH problems, you just worry about the first ionization and you are good to go. You knew that there was going to be an exception in there. So let's talk about that exception. That exception is sulfuric acid, because sulfuric acid is polyprotic, but H2SO4 is also a strong acid, and that means that the first dissociation occurs 100%. So here's what you have to realize. If you've got a solution of H2SO4, you actually have 0 H2SO4 that's actually present, because it's a strong acid. It's going to 100% dissociate. This means what you really have a concentration of is HSO4 minus, hydrogen sulfate, which is in itself a weak acid. So that is totally present. But of course, a weak acid will, to some small degree, dissociate, producing its conjugate base, in this case, sulfate. So you need to be aware that both hydrogen sulfate and sulfate are present, but there's going to be a lot more hydrogen sulfate. But of course, the sulfate is still present in higher concentration than the H2SO4, because that's not present at all. So a sulfuric acid solution is a combination of a strong acid and a weak acid together. But do you want to hear the good news? The good news is that because sulfuric acid is a weak acid in its second dissociation, the second dissociation contributes a negligible amount when you have concentrations less than 1 molar. And the happiest part of this is that the AP test only considers quantitative calculations for sulfuric acid concentrations less than 1 molar. So basically, or acidically, I suppose, as it were, if you're given a calculation for H2SO4, you treat it as a strong acid and you are done. Now, you could totally be asked qualitative questions about the relative concentrations, but quantitatively, we are allowed to just treat H2SO4 as a monoproduct strong acid. So, since it's a strong acid, that of course means that the initial concentration of H2SO4 is going to be the concentration of HSO4 minus at equilibrium, 100% dissociation, right? Which is what gives us your concentration of protons, and that's what you use for pH. So exactly what you would do with a strong acid. All right, and that's all you need to know about calculating pH for a mixture of weak acids or a polyprotic acid. So thank you for playing with the glories of chemistry.